Station. This is Melanie Cowan at ESTEC. How do you hear me?
Tech, this is station. I'm reading you 5 by 5.
Thank you, Frank. It is now time to begin the event. You are connected with Barcelona, Mechlin, Milan, and Thessaloniki. Please begin the demonstration.
Okay, first of all, welcome everybody in all those exotic places all over Europe. It's a pleasure for me to be with all of you from on board the International Space Station, and congratulations, of course, to all the people that participated in these events. As you can see, I have here next to me the mass measurement device demonstration, and I'm going to show you how we could, or how we can, measure mass in weightlessness. Because of course we are here on board of the International Space Station. We are in weightlessness environment. As you can see, I can move my feet from the ground and I can just float. It's something that you can't do on Earth. However, my mass is still the same as the one that I have on Earth. So how do we measure mass on orbit? Well, actually, we can use springs for that, because mass maintains its properties if it's in a gravitational field, if it's on Earth, if it's on Jupiter or somewhere else. Mass maintains its properties. And what we can see is, if we look to springs, every spring has its own properties as well. And the frequency to which a mass is oscillated on a spring depends on two factors. Basically, it depends on the spring itself, and it depends on the mass that is attached to the spring. And since we very well know the spring here, we can try to measure the mass that we have attached to the spring here. So let's start with the first measurement. Here now attached the biggest mass to these springs. I have a chronometer, and I will deflect the mass, and I will try to let it oscillate for about 20 times, something that we can easily do on orbit. I know that on the ground it's a little bit more difficult to do it so many times, but I will let it oscillate 20 times, and I will count how long it takes for it to oscillate 20 times. Okay, that was 20 times, and on my stopwatch here, I have a timing of 8.9 seconds. So let's fill out our table and let's see what that gives us. My first timing 8.9 seconds and 20 oscillations. If we divide 8.9 by 20, we get exactly the period of the oscillation. Actually gives us 0.445 seconds. With the formula of our spring, with the spring constant that you can see here on top, we can now calculate the mass. Delta is 0.75. Of course, in our standard units, which is in kilograms. So the mass that I've measured here would be around 75 grams. Try to read this and see if you can get the same results. Pretty close. This time I have 8.8 seconds. This is a period of 0.44, so I will now try to calculate the mass again. And it gives me 74 grams. So you see that even with this crude method of measurement, we can get quite a good accuracy. See what would happen if we now read the mass. From this formula, where we can see that the mass is equals 0.3 times the period squared, if the mass is reduced, then the period should be reduced. Actually, so that means that it should oscillate fast. Let's see if indeed our mass will now oscillate fast when we reduce it. This time I measured timing of 6.9 seconds. So indeed, it oscillates a lot faster, as you probably also could see on the video. So let's see what that gives us as a mass. That gives me a mass of 44 grams. If we can also repeat this test. This time I had 7.5 seconds, so a little bit longer. Gave me a mass of 53 grams. You can see